In this video, we shall look at a couple of review problems associated with Coulomb's law. First, a brief introduction on Coulomb's law. Let's assume we have two charges. Let's call this charge Q1 a positive charge, and another charge Q2, also a positive charge. The separation distance between them is, say, r. Since these two charges are positive charges, they are like charges, they will repel each other. The force on Q1 due to Q2, let's call it F1, and the force on Q2 due to Q1, let's call it F2, have the same magnitude. And this magnitude, F1 or F2, is given by the following expression. It is a constant K times the product of the strength of the two charges Q1 times Q2 over the square of the separation distance r squared. Now K is a constant whose value is 9 times 10 to the power 9 in a unit of Newton meters squared over Coulomb squared. This expression is known as Coulomb's law. Force is a vector, so naturally we need to identify the direction of F1 and F2. The direction of F1, since it is a repulsive force, it's going to the left, and you can represent it with a unit vector minus I hat. I hat is a unit vector along the positive x direction, minus I hat is a unit vector along the negative x direction. Likewise, the direction of F2 is just I hat. What if both charges are negative charges? Now they are still like charges, and like charges repel, so the direction of F1 is the same, namely going to the left, and direction of F2 is going to the right with this much magnitude. Now let's make one of the charges positive and the other one is negative. Now they are opposite charges. Opposite charges attract each other. So the direction of F1 will be going to the right, and the direction of F2 will be going to the left, since now the two charges attract each other. The magnitude is still given by this expression. Next, let's see how to apply these concepts to problems. Problem 1. 3-point charges, that is Q1, Q2, and Q3, lie along the x-axis as shown in figure below. The positive charge Q1 is 15 Coulomb in its strength, and it's located at x equals to 2, so the location or the coordinate is x equals to 2. Measured in the unit of meters. Q2 is also a positive charge whose strength is 5 Coulomb, and it's located at the origin. If the resultant force on the third charge Q3 is 0, find the coordinate, namely find this point L. So let's look at the free body diagram for the system. Now Q3 is a negative charge, so it will be attracted to Q2, and that force is going to the left, and at the same time it will also feel an attraction from Q1, namely to the right. Let's call the leftward force F2 and the rightward force on Q3 F1. So let's write down F1. F1 is going to the right, so it is represented by unit vector I hat. The expression is given by K, which is the constant that we introduced earlier. The product of the two charges, namely Q1 and Q3. Q1 is 15 Coulomb. Q3 we don't know, so just write it as Q3, over the separation distance, which is 2 minus L, and square that. So this is Coulomb's law for Q1 and Q3 pair. Now let's write down the expression for F2. F2 is heading leftward, so that means it is represented by unit vector minus I hat. The expression is again K, the constant. The strength of a Q2 is given to be 5 Coulomb. So 5 times Q3, which we don't know, over the distance between them is just L, and square that. We are told that the resultant force on Q3 is 0. What that means is F1 plus F2 is 0. They have the same magnitude, but opposite direction. So equating the magnitudes, we get the magnitude of F1 is K times 15 Q3 over 2 minus L squared equals the magnitude of F2 is K times 5 times Q3 over L squared. You see that K cancels out, Q3 cancels out, so that's why we don't need to know the magnitude of the strength of that third charge, and we end up with this equation. Let's cross multiply this equation to turn it into a normal quadratic equation. So you get 15L squared equals 5 times 2 minus L squared, which is just 15L squared equals 5. Expanding the bracket, you get 4 plus L squared minus 4L. Rearranging the terms, you get 10L squared plus 20L minus 20 equals to 0. Dividing the entire equation by 10, the first term is L squared, the second term is just 2L, the third term is just 2. You see, this is a quadratic equation in L, and we can solve that using the quadratic equation formula. So L is minus 2 plus minus square root 2 squared minus 4. A is 1, and C is minus 2 over 2A, so that's 2. And you choose the positive solution because L is a positive number, and you will get 0.732 meter as the answer. So the coordinate for Q3 is x equals to 0.732 meter. And that solves the problem. Problem 2. Two identical small charged spheres, each having a mass of 0.02 kg, hang in equilibrium as shown below. So these are the two charges. The length of each string, L, is 0.2 meter, and the angle alpha is 5 degrees. Find the magnitude of the charge on each sphere. So you want to determine the strength of charge in Coulomb. So basically what is happening is, since these two charges are identical charges, so let's give them some sign. Let's call them plus and plus, or negative and negative, it doesn't matter. So since they have like charges, what's going to happen? They will repel each other. And there is also tension in the string. So in this string you have tension going like that and like that in the second string. So the horizontal component of these tensions will balance the electrostatic force given by Coulomb's law. And that is the idea behind this problem. Now this is a two-dimensional problem, so you have to be careful about components of forces. So let's look at the free body diagram. It is sufficient to look at just a single charge. So let's look at the left side charge. So that's your charge right there. What are the forces acting on this charge? The first one is the weight. We know the mass. The mass is given by 0.02 kg. So the weight is 0.02 gravity. G is 9.81. The second force is the electrostatic force that is pushing the leftward charge to the left. Let's call it F. And the third force is the tension in the string that's going in that direction. Let's call it T. Let's balance all the forces. So that is the y-axis and that is the x-axis. Let's look at the y components of all these forces. There are only two. The first one is weight, and the second one is the y component of the tension. So they must balance each other. So the y component of the tension equals the weight. What is the y component of the tension? It is just the tension times cosine of that angle. So that angle, this angle right there, is the same as alpha. So T cosine alpha, alpha is 5 degrees, equals 0.02 g. So that's equation 1. Now we need one more equation. To write down the second equation, we need to analyze the forces acting along the x-axis, and there are only two. The first is the Coulomb force, which is acting along the leftward direction, and the second force is the x component of that tension, which is going in a rightward direction. So you say T sub x, the x component of the tension, equals F, which is the electrostatic force between these two charges. Now what is x component of the tension? X component of the tension is the tension times the cosine of that angle. So it's that angle, basically. If alpha is 5 degrees, then this angle here is 90 minus 5, which is 85 degrees. So T sub x is T cosine 85 degrees. Electrostatic force is given by Coulomb's law. It is the constant K, whose value is 9 times 10 to the power 9 in SI units, times the product of the two charges Q and Q. We don't know, that's exactly what we want to determine, the strength of the charges, over the square of the separation distance. The separation distance R is that. So R will be this distance times 2. So what is that distance? It is just L cosine of that angle, 85 degrees, times 2. L is the length of the string, which we know to be 0.2 meter. So R is 0.2 times 2, which is 0.4, times cosine of 85 degrees. So the right-hand side is just kq squared over 0.4 cosine 85 squared. And this is equation 2. Substituting the expression for t from equation 1 inside of 2, you will get t is 0.02 g over cosine 5 degrees times cosine 85 degrees equals all this, which is kq squared over 0.4 times cosine 85 degrees squared. We know the value of k, it's given there, and we can determine the value for q. And when you calculate the value for q, you get 4.8 times 10 to the power minus 8 Coulomb. And that's the answer, and that solves the problem. Thank you for watching.